So resolving displacement, and in this case I could just say resolving some, we don't want necessarily say a vector, but it is going in a particular direction, which is where we're going to be looking at either a negative or a positive value. So in this, I want to do an example. It's a simple example. I found it in a textbook years ago. Thought it was really cute, and I always use it to sort of kind of start off what we do in physics when we get to this part of it. So just keep in mind that motion has an x and a y component. Up until now, we typically avoid that concept because we assume everything's being constant and we just look at motion directly along an x or directly along a y. But now we realize that we don't move just straight this way and straight this way in life. We're kind of always shifting about. And so our displacement, or where we are when we stop moving or at any particular point, is a straight line distance, but it is at some angle to where we started, in reference to the ground, in reference to the ceiling, whatever the case may be, to a wall, whatever the case may be. We just have to define that in our free body diagram. So let's take a look at this example and take notes. I love hummingbirds. Birds are really, really cool. That's probably why I like this problem. So I found this problem in a book years ago, and I guess because I saw the word hummingbird, it just attracted my attention. It's a fairly easy problem, but it helps define very early on a really good example on how we resolve all of our vectors. So you got a hummingbird, it's flying horizontally 9 meters, and then all of a sudden it goes upwards 3 meters towards this really beautiful flower. Envision one in your mind. What's the bird's displacement? So you guessed it, we need a free body diagram. So let's get a free body diagram on this thing right here. So I don't know, first, I don't know, I'll draw yourself a bird, and I know that we're supposed to sort of draw these things out of their environment, but I want a bird on this. So, but the bird is going to start here at some point. It goes 9 meters, then it goes up 3 meters, and now notice I drew that vertical component a fraction of the horizontal. You want to try to draw them kind of sort of to scale if you can. It helps with visualizing what's going on. We should then remember that we're going to have a resultant, and that resultant in this case will be our displacement, right? So, right, oops, I did not mean to erase, I meant to highlight. So the resultant right there, that's going to be our displacement. So we already know that right here, this is our displacement. Here we've got a change in y equals vertically 3 meters, right? And our change in x equals 9 meters. 9 meters. All right. Well, you remember the whole, oh, don't forget, we have to do this. I tend to forget this myself because I take it for granted, but you do have to define your coordinate system every time you do this. So don't forget, you remember the whole a squared plus b squared equals c squared deal. That's what we got. We've got a situation here, a squared plus b squared. Now, we're at some angle theta. We don't know what that is, but we can resolve that here in a little bit. All right, we could resolve it now and get it over with, but we're going to do that later. All right. So we've got the whole a squared b squared thing. So let's go ahead and do that. So in this case, I don't know. So we've got the c squared is basically going to be the hypotenuse, the d. So let's just basically what we have is a change in x squared plus a change in y squared is going to equal the displacement squared. All right. This match, you can see that this basically matches up to that. All right. So ultimately we're solving for d. So I'm going to just reorder this. D squared equals x squared plus y squared. And I'll take the square root of that towards the end. You can take the square root of it now and just have it, or just do it at the end. It doesn't really make a difference. So our x squared is 9 meters, and that's going to be squared plus y is going up. So remember, we've got a vertical displacement of 3 meters. So and according to our coordinate system, we defined this as being positive and this as being negative. So we know we don't have to assign any negative values in this particular problem the way it's being drawn. We assume it's flying forward. You don't assume it's flying backwards unless something in the problem tells you that. All right. So now let's go to our calculator. What do we got here? We've got oh, never mind. Oh yeah, never mind. 9 times 9, 81. So that's 81. Can't believe I did that. So that would be meters squared. So both the unit and the value are squared. And then, of course, this was squared. I forgot to put that there. So 3 times 3, that is 9. So we'll put meters squared. So this right here equals, what is that? So that is 90.0 meters squared. And this is d squared. So this is a hypotenuse. We have to resolve that by taking the square root of both sides. So we've got d, our displacement in this case. So that would be 90, enter, second, square root, second answer. We get 9.48683 and a whole string of other numbers. We just need extras. We don't need all of that. And then it also takes the square of the unit. So we're looking at D is approximately, we're looking at about 2 sig figs on this. So we're at around 9.5 meters. So the displacement of the hummingbird from where it started to where it goes to meet the flower, so we can get some of that sweet, wonderful, delicious nectar, about 9.5 meters. All right. More specifically, we would say probably 9.48. We'd go with something like that. We would probably assign an extra 0 to our number so that we could have an extra significant digit, because 9.48, 9.49 would actually be a better value. But for this problem, we're going to stick with what we've got. So now we know that this hummingbird is 3 meters up and 9 meters over from its starting point, but is at some angle theta. That's where our trig comes in. That's where we need to use some trigonometry. So remember I said we're going to use, we have our y and our x value. Since we know we have our y and our x value, then that means we are going to be using our tangent function, right? So tangent theta equals our change in y over our change in x. Remember TOA, tangent, opposite over adjacent. All right, so in this case here we see tangent theta, the change in y was 3 meters, change in x is 9 meters. So I'm just going to replace that and put 3 meters over 9 meters. Now to get an angle, you take what is called the inverse tangent. So theta is going to be the inverse tangent of 3 meters divided by 9 meters. Let me scroll that up for you. All right. So now you should notice on your calculator, if you find the tangent button above that, you'll see a symbol that looks like this, TAN -1. That's your inverse tangent. And so you just hit your function button, like the second button, so that you can go up to that. All right. So we're going to go second tangent. Oh, I'm sorry, I hit sign by accident. Second tangent, and then we've got 3 divided by 9. That gives us theta is 18.4349 and a whole bunch of other numbers. Good thing I'm finishing this. You see I have office hours. All right, and then of course that's degrees. So let's resolve this down to a value consistent with what we had up here, 9.5 right here. So if we just say 18, that doesn't sound, that's not as accurate as we really could be. So we should go with 18.43 degrees would be more accurate. Again, you could add zeros. We could make this 3.00. And that makes it 18.4. We could go 3.000, 3.000, yeah, 3 after that, and you have 18.43. All right, it depends on the situation. So we've got 18.43 degrees. That is theta. So the final answer for this, what is the bird's displacement? We have two components to the answer. We have the displacement and we have the angle of displacement. So a good final answer for this is the bird's displacement comma D equals 9.5 meters at 18.4 degrees above the horizontal. I know that's a lot, but you have to do that. This bird is now 9.5 meters away from its starting point. That's its displacement. So if it started here, so if it starts here, it is 9.5 meters away from this point. So there's displaced. There's the final. There's the initial. It is 9.5 meters away. I had to check my computer. It is 9.5 meters away, and it's at an angle theta of 18.4 degrees above the horizontal, so above the x component of, in other words, the ground. It's above the ground. Go do some physics problems. Take this, backwards engineer it, and just know that every single time you're resolving your x and your y component, getting your resultant, your hypotenuse, and just plugging and chugging away. So it's fairly easy math. We're going to be using the same process over and over again. Just going to be using it for things like velocity and force and things like that. So hope that helped. So remember, when something's in motion, there's x, there's y, from whichever direction you come from. We just always assume a forward direction unless there is something about what we observe or what we're reading in the problem that implies that there is motion in an opposite direction of what we consider forward. So any direction, any movement is considered forward unless otherwise defined as not being forward, which would be backwards or something. Or it's to the right, which is positive. We don't assume to the left, which would be negative. So keep that in mind. And then it's just a matter of using your simple trig functions for defining the x and the y components and your hypotenuse, which in this case happens to be like a displacement. So hope it helped. Be on the lookout for some more videos. I'm going to be doing more examples for you. It just brings us back to our pre-calc and some geometry where we're using trig. A lot of what we're going to be doing will be right angle math, and right angle math is pretty easy. So if we have something greater than 90 degrees, I'll have problems and show you how to do that. And there's actually a couple of ways or so. There's multiple ways to resolve those problems. There's not just one way. And we'll take a look at that when we get to that. For now, let's focus on some right triangle math, a little bit of trig. Just makes it kind of spices things up a little bit. It's good seeing you. Stay curious, and I'll see you in the next video. Bye.